now we're going to look at the stream challenge, which is going to be a weak acid versus a strong base. Okay, so for the weak acid strong base, it's going to be 50 milliliters of the weak acid, acetic acid, 10th molar. And notice you're given the case of A for it, 1 times 10 minus 5, versus the strong base, 10th molar sodium hydroxide. You'll be happy to know that molarity times volume equals molarity times volume works whether it's strong or weak. So if you look at the math of that, if you solve for X, you notice that 50 milliliters of sodium hydroxide will be the endpoint. Okay, now the start is a little bit more difficult in a weak base because you have to do a weak acid, you have to do a weak acid equilibrium problem. So the weak acid, acetic acid, is going to break up into hydrogen acetate, and you're given the case of A 10 to minus 5. Okay, the start step is you're given 10th molar acid. Okay, and because of the small k, notice that's also the completion step. Now the change step is you're going to lose some of the molecules of acid, get some hydrogen and acetate. So at equilibrium, you've got 0.1 minus x and x and x. Okay, so plugging into the case of A, if you solve for x, you'll get the concentration of the hydrogen ions. Okay, I think my math is correct. It'll be 10 to the minus 3, and therefore the starting pH will be 3. Okay, so that's pretty straightforward. Now here comes the tricky thing about doing a weak acid titration. The titration equation itself is kind of tricky. So the reaction is you have molecules of acetic acid plus sodium hydroxide, gives you the normal neutralization, water and a salt. The salt is sodium acetate. Okay, now when you go to the ionic and anionic equation, it's a little bit tricky. Okay, so look at the second line here under the titration reaction. Okay, so acetic acid being a weak acid really stays mainly in molecule form, doesn't break up into ions. Sodium hydroxide being a strong base breaks up into sodium and hydroxide, that's to be expected. The water stays as molecules, and the salt sodium acetate breaks up into ions. Now notice the interesting thing is there's only one spectator ion there, and that would be the sodium. So notice the net equation. Okay, so the net equation will be molecules of acetic acid plus hydroxide give you water and acetate. Okay, so that is the equation going to be used for figuring out the points on the titration curve. Now, we need the K for that titration reaction. And I think that's one of the trickier things in the course is how do you get the K titration? It's too bad there's no table you can look at. No one ever devised a table. Now, the thing is, if you look at the titration reaction, the forward reaction is not useful in terms of visibility, but look at the reverse reaction. You're putting acetate into water, and you get hydroxide. So the name of that reaction would be a K sub B of acetate. Now, it's the reverse reaction, so therefore we write it as 1 over K sub B of acetate. So the forward reaction would be 1 over the reverse. Now, look at the line below. So it's going to be 1 over. Now, notice Berg did not give you the K sub B of acetate, and you won't find that in a table. So remember, you have to give it one more chance to get it. Remember, K sub A times K sub B is K sub W. So doing the algebra, then K sub B would be K sub W divided by K sub A for acetic acid. And if you rearrange that mathematically, notice it's going to be K sub A of acetic acid over K sub W. Now, I guess I could ask you to write that on an exam. I probably will not, but you'll have to know what it is. And here's a cute little trick. If you look at it, notice it's A over W. K sub A over K sub W. So think alphabetically, A over W, and therefore you can get the K for the reaction. So the K sub A for acetic acid is given as 10 to the minus 5. You know K sub W is 10 to the minus 14th. Do the math on this, you get an answer of 10 to the 9th. Now here's a good double check. Titration reactions are always favored. Acid and base always want to get together, form nice stable water, and therefore you should get a positive value, and sure enough, it is 10 to the positive 9. Okay, so what you're looking at is, in red is the strong acid, strong base curve that we got from Tuesday. And notice what I added to it is, notice the start. The starting pH of a weak acid is 3. So it was 1 for a strong acid, notice it's 3 for a weak acid. Okay, now I don't get it. They're both 10th molar. If you look at the top, it was 10th molar hydrochloric acid, 10th molar hydrochloric acid, and 10th molar acetic acid. Shouldn't the pH be the same? No, because the weak acid doesn't break up completely, and therefore notice you get a higher pH for the start of the weak acid versus the strong acid. Okay, so now we're going to get some more points on the titration curve. So we're now going to go to halfway to the end point. We're going to add 25 milliliters of sodium hydroxide and figure out what the pH would be. Now notice I've written the titration equation again. Let's go over it. So I have molecules of the weak acid plus hydroxide gives you water and the conjugate base. And again, I've repeated the case of T is 10 to the positive 9. Okay, so here comes the mathematics of this. The starting situation is 10th molar acid, 50 milliliters, 10th molar base, 25 milliliters. You must take dilution into account. So notice the total volume is 75. So dilution factor is 50 over 75 for the acid, 25 over 75 for the base. You do the math on that, you get 0.66 molar, 0.066 molar, and 0.033 molar for the acid and the base. Okay, the completion step is definitely to the right because of the high size of the large size of the K. So going to the right, the limiting chemical is all the base gets used up, and you have some excess acid. Okay, notice you form some water, even though we don't care about that, and we're going to form some of the acetate, the AC minus. Okay, now you can't have the zero, so that's why in the change step it's going to go to the left, and dealing with x's minus x, plus x, and plus x. So at equilibrium, you've got 0.033 plus x for the acetic acid, x for the hydroxide, water we don't care about, and 0.033 minus x for the acetate. Now, how are we going to get pH? The obvious thing would be to solve for this x right here and get the hydroxide ion concentration, and therefore get the POH and therefore the pH. Now, the experts have decided there's a faster way to do it, and it goes like this. Besides the titration equation taking place, you have another system going on, and that is the weak acid itself is going to be in equilibrium with hydrogen ions and the conjugate base. And the experts decided they're both taking place. It's easier to use the bottom one to get the pH. Now notice we're going to go right to equilibrium. So we have the equilibrium concentration of the acetic acid, 0.033 plus x. I transfer it over to this equation here. Let's call the hydrogen concentration y. And the acetate, again, we're going to transfer as 0.033 minus x. Let's plug these three into the mass action expression. So the K sub A 10 to the minus 5 will be hydrogen concentration times acetate divided by the acetic acid concentration. Okay, I've circled the x's we're going to ignore, and notice a wonderful thing. The 0.033's cancel out, so the hydrogen concentration is equal to y, which will be just the K sub A 10 to the minus 5, and therefore the pH will just be 5. So let's see how the titrations compare at this particular point right here. So the red is the strong acid, strong base. You're seeing the beginning of the weak acid titration. So we know the start was pH was 3, and now we got halfway through it as pH of 5. Now notice that it actually curves upward, so you do not draw a straight line between them, but it actually curves very quickly upward and then starts to level off. You'll find out later why it has that particular shape. Okay, so now I'm checking to go to the endpoint. So we're going to go a little bit before the endpoint. We're just going to add 49 milliliters of the sodium hydroxide. Okay, so you've kind of seen this math before. You start with the titration reaction. We need its K, which is 10 to the 9th. And we're starting with 10th molar acetic acid always 50 milliliters of it. But now Berg wants you to take 10th molar sodium hydroxide and add 49 milliliters of it. Taking dilution into account, the total volume is so close to 100. Let's use 100, because we're just trying to get the shape of this thing anyway. So taking dilution into account, the starting concentration of the acid is 0.05 molar. The base is 0.049 molars. Okay, we're going to shove this all the way to the right. The limiting chemical is the hydroxide, so all it gets used up, 0. And notice there's some excess acetic acid, 0.001 molar. This is going to form some water. We don't care about that. And notice the acetate form is going to be 0.049 molar. Okay, you got to back up a little bit because we can have the 0 in the system. So now using x's, minus x, plus x, plus x. Okay, and drawing these summation lines, we find out the equilibrium concentration of the acetic acid is 0.001 plus x, hydroxide is x, and the acetate is 0.049 minus x. Now we could solve for this x right here, get the hydroxide, pOH and pH. It's faster though to use the dissociation of the molecule of acetic acid itself. Okay, so the case of A for that is 10 to the minus 5. Transferring then the equilibrium concentrations above. So this is the equilibrium concentration of that. Sorry, I didn't print too well. It's 0.001 plus X. Y is the hydrogen, and 0.049 minus X. Plugging this into the mass action expression, the case of A 10 to the minus 5 is equal to hydrogen times acetate divided by acetic acid. Okay. And while you're kind of digesting that, I'm going to see if I did the math on that correctly. So let me try this on my calculator. Okay, so the Y should be equal to 185 minus times 0.001 divided by 0.049. Okay, and I get an answer of 2 to the minus 7. Okay, that's the value of the hydrogen concentration. So I'll hit the minus the log of that, and I get a pH of 6.69, so 6.7. So yes, the math is correct. So hopefully that all makes sense to you. Okay, so here's what our titration curve looks like so far. Okay, so the starting pH was 3, it then went up to 5, and now it went up to 6.7. So we're not quite at the end point yet. And notice the main thing to notice is the weak acid titration curve is above the strong one. It's higher because it's a higher pH because we're getting fewer hydrogen ions since it is a weak acid. Okay, so now we're going to get to the end point. And I must admit, I think this is one of the hardest parts of the whole course is to get the pH, the end point of a weak acid, strong base titration curve. So notice the first thing that's written here is the net equation. Molecules of the weak acid plus hydroxide gives you water and acetate. Okay, and in the case of T, we worked out before, is 10 to the 9th. Okay, so taking dilution into account, okay, 0.1 times 50 divided by 100 gives the diluted concentration of the weak acid, and 0.1 times 50 divided by 100 gives you the base. Now remember, this is a great double check. If you really, really think you're at the end point, these concentrations have to be the same. Which means what's going to happen in the completion step, they're both going to be used up completely. So there's none of these 0, 0. We're going to get some water. We don't care about that. But notice we're going to get 0.05 molar of the acetate. That's going to be very important later. Now we went too far, so the baby back up in the change step is minus X plus X plus X. Okay, so the concentrations at equilibrium are X for the acid. I'm going to draw this, add additional line here. X for the hydroxide. Okay, water we don't care about on 0.05 minus X. Let's try that cute trick we did before. Let's plug these into the other system, which is the breakup of the acetic acid. So the equilibrium concentration of the molecules is X. Let Y be the hydrogen, and 0.05 minus X is the acetate. Now you should notice a major problem at this point. There's two unknowns. We don't know X, and we don't know Y. So here's a case where we cannot use the shortcut. We must use the titration equation itself to find out the value of X, which is going to give us the hydroxide ion concentration. So we're going to have to get pOH, therefore pH. Okay, so going to the case of T, the 10 to the 9th is equal to products over reactants. Denominator right water. So the product is going to be the acetate, the 0.05 minus X, and then we have the molecules of acetic acid, X, and hydroxide. Okay, notice we can ignore the X next to the 0.05 is going to be small. So X squared is going to be 0.05 divided by 10 to the 9th. Did I do my algebra correctly on that? I think that's right. Okay, and let me check my calculator to see if this is right. So I get 7.07 times 10 to the minus 6. So X is going to represent the hydroxide ion concentration. Notice it doesn't do any good to represent the molecules of acetic acid. We need hydroxide ions. Okay, so I'll take minus the log of that. So the pOH is 5.05, subtracted from 14, and the pH is 8.849 or 8.85. Now I've got an interesting question for you. If this is the end point, how come the pH isn't 7? How come it's 8.05? Isn't that kind of weird? It's supposed to be neutralization, and yet we get a basic pH. Anybody have any ideas why that would be so?